Same cylinder, same wind, two different meshes. Watch what changes. Coarse mesh up top, and the wake is just a blur. Fine mesh below, and the same flow breaks into a clean row of vortices. Whether you ever see them comes down to the mesh. The mesh. It's where the equations actually get solved. Here's where we're headed. First, what a mesh actually is. Then a case we can check by hand, the pipe, straight from Navier-Stokes. We'll turn the calculus into arithmetic, solve it, and watch it converge. Then back to the cylinder, to see if the mesh catches the vortices. And we'll finish with what makes a cell good or bad, why walls need thin cells, and the main types of mesh. So what is a mesh, really? You chop the domain into little cells. The solver keeps one number per cell, and that's all it ever knows about the flow. More cells, more detail. That's basically the whole game. Before trusting any of this on the cylinder, let's test it somewhere we can check the answer ourselves, a plain pipe. Start from the law behind every flow, Navier-Stokes. One equation keeps mass conserved. The other says the fluid accelerates when pressure, friction, or gravity push on it. Now whittle it down. The flow is steady, so the time term goes. It's fully developed, the profile is the same all along the pipe, and there's no crossflow, so the whole convection term is exactly zero. Fold gravity into the pressure, and one balance is left, the pressure push against friction across the pipe. The pressure drops at a steady rate down the pipe, so that push is just a constant, divide through by density, and this is the equation we actually solve. Now it's a simple ODE. Integrate it twice. Each pass leaves a constant behind. The walls pin those constants down. The flow sticks to each wall, so the speed is 0 at the bottom and 0 at the top. 0 at the bottom kills one constant, 0 at the top sets the other. And what drops out is a parabola, 0 at the walls, fastest down the middle. That's our exact answer to check against. The equation wants a second derivative, but all the computer has is the value sitting in each cell. So we rebuild the derivative from those. Write the neighbor on each side as a Taylor series. Add the two together, the odd terms cancel out, and you're left with twice the center value, plus delta squared times the second derivative. Rearrange, and the second derivative is just 3 neighboring cells, subtracted and divided. All we dropped is the error, and it falls like delta squared, half the cell, and the error drops to a quarter. Put that on the mesh and solve. Each cell holds 1 bar of the profile. And because the pipe is simple enough to solve by hand, we know the true answer, the white parabola, exactly. So we can see precisely how wrong the mesh is. Coarse cells are blocky and sit off the curve, and that red gap is the error. Shrink the cells, and the staircase snaps right onto the curve. The red gap closes, and the error falls away. How fast does that error fall? Plotted against cell size on log axes. A straight line, slope 2. The error really does fall like delta squared, exactly what the derivation said, so you keep refining until the answer stops moving. That's mesh independence. Now the real thing. Behind the cylinder, there is no formula to check against. A coarse mesh smears the wake, and the shedding just vanishes. Refine it, and the full vortex street shows up. So you do the same thing as before. Refine until the flow stops changing. Mesh independence on a flow you could never solve by hand. Not every cell is a good cell. A near square one behaves. Skew it, or stretch it long and thin, and accuracy slips. 2 numbers tell you how bad: aspect ratio, the long side over the short side, and skewness, how far it's bent out of square. To get the flux through a face, you need the gradient across it. Taking the plane difference of the 2 cell values only works when the line between their centers meets the face square on. Tilt that line by an angle, and the difference misses part of the gradient. You patch it with a correction term, and the more it tilts, the bigger that patch has to be. That's the price of skewed cells. The walls need care. Right next to one, the speed shoots from 0 at the surface up to full speed across a very thin layer. To resolve that, you pack thin cells against the wall and let them grow outward. How thin the first one is, you set with a number called Y+. 2 big families. Structured grids, tidy rows of quads or hexes. Cheap and accurate, but a pain to wrap around a complicated shape. And unstructured grids, triangles or tets, that'll fit just about anything, though you pay in cell count and a little accuracy. Most real meshes mix the two. So, to pull it together, a mesh is just the cells you solve the equation on. The calculus turns into arithmetic over neighbors, with an error that falls like delta squared. On a real flow, you refine until nothing moves. And good cells, thin cells are the walls, and the right type of mesh are what hold it all together. That's all for this video.